One of the other use case of singular value decomposition is to obtain a low rank representation of any matrix. We know SVD is A is equal to U sigma V transpose, and we can obtain AK, which is the kth rank approximation of the matrix A by using SVD. One of the theorem states that SVD gives the best kth rank matrix as compared to any other kth rank matrix, in the sense that it will have the least Frobenius norm, which is stated using this theorem called as Eckhart-Young theorem, which states that the best low rank approximation AK of a given matrix A is found by truncating its SVD to its first k largest singular values and their corresponding singular vectors. So the best in the sentence mean that the error between the A and AK computed using Frobenius norm is less than any other matrix BK. So if you take the kth rank approximation of all matrices and if you compute the error with the A matrix, the matrix which is obtained using SVD, which is AK, will have the least error as compared to any other matrix. That's what this theorem states, and in that sense SVD gives the best kth rank approximation of any matrix. So this low rank approximation can be obtained using SVD as follows. So as we stated, we will, rather than taking all the singular values, we will be taking the first k largest singular values and its corresponding singular vectors, and we construct U and V matrix and thereby construct AK vector. So we are not using all the eigenvectors, we are just using the k largest singular values and its singular vectors to obtain the rank k approximation of a matrix. So let us now see one example for computing the rank k approximation of any matrix. Let's take this matrix A, which is of rank 2 and the singular values are root 3 and 1, and if you compute the singular vectors for the largest singular value, which is root 3, we get U1 and V1 as follows. And this V1, as we stated earlier, which is obtained by using the orthogonality property of eigenvectors. And once we obtain the largest singular value, we can get the best rank 1 approximation of this matrix by constructing U sigma V transpose, but using only one singular value and one singular vector. So when you compute this is what we get it. This is the rank 1. As you can clearly see, there is only one independent column vector, and this is the rank 1 approximation of the matrix A. So this is the final answer. Our original matrix was rank 2 and we obtained the best rank 1 approximation of the matrix A. So in this way we can obtain for any matrix. We'll take one more example. So here we have matrix A with rank 2, and this is what we found out just now. This is the rank 1 approximation of the matrix A. Let's take another example with the dimension is 3 cross 4, which is of rank 3. So there are 3 independent vectors. This fourth one is a dependent vector. So we have 3 singular values, non-zero singular values, and if you see the rank 2, best rank 2 approximation of this matrix and rank 1 approximation of this matrix, it will be as follows. This is the rank 1 approximation of the matrix computed using SVD by taking only the largest singular value, which is sigma 1 equal to 2, and keeping all other singular values as 0. Best rank 2 approximation of a matrix can be obtained by retaining the 2 largest singular values, which is sigma 1 equal to 2 and sigma 2 is equal to root 2. As you can see here, A2 is the best rank 2 approximation of the matrix A. So in this way we can obtain the kth rank approximation of any matrix of any dimension by using SVD. Let us see one application in the domain of image processing where we can use this idea to compress any image. So A has been expressed using singular value decomposition, and where here we want to use this image, which is a real image, and we want to convert into grayscale and apply SVD and retain only few singular values and see how the representation and the output would be, and how it will be helpful for us in image compression. So let's I'll show this demo. As you can see here, we have 4 singular values. Now a lot of blurriness, 8 singular values, this is the output. And when you take 16 singular values, as you can see, almost the details are visible. 32 singular values, we have this kind of a image with 64, and 128 singular values, we will have almost near to the clarity without losing much of the details. 256 singular values, 512 singular values, and we are hardly seeing any differences towards the end when we are introducing lower and lower singular values. So in this way we can use SVD low rank approximation for image compression. Let us now see how we can implement the rank approximation of a matrix using SVD in Python. We are using here NumPy library. This is the input matrix A, which is of dimension 2 cross 3. We are invoking the linalg and SVD function, which is part of linalg library, to compute the U, sigma, and V transpose. And we reconstruct this using here. So if you observe the output, this is the input matrix A, U matrix is this, singular values of are 1.73 and 1, and V transpose is this. Note that there is no third row in V transpose, because we have third column in singular value matrix as zeros, so there is no use of putting this. You can control that by changing from false to true and appropriately adjusting the code. So the reconstructed matrix, if you see, it is exactly similar as the original matrix because we have used all the singular values. Now let us see how we can represent rank approximation of a matrix using SVD. So as we have computed U sigma V transpose, we can take k is equal to 1 and obtain the rank 1 approximation of the original matrix. So when you take only one singular vector and one singular values, you will be getting U1, UK, SK, and V transpose. So we will be using this one singular vector and one singular values to reconstruct the matrix AK, and this is how it looks like. As you can see here, this matrix has only one independent vector, and the rank is 1. So we got the best rank 1 approximation of the original matrix using SVD, and we can implement in Python as given here. Let us now discuss how SVD can be used for image compression by using the low rank representation. So here we have written code in Python. So this is, we are loading the NumPy and Matplot libraries here. We are also using SK image library. First we try to read the image. So we have used a image which is loaded already here. And we computed all the 3 components, RGB components, and we apply SVD for each of these components through this method. And once we obtain SVD for each of these components, we try to reconstruct for with just 100 singular values and see how the output image would look like. So we have plotted both the original image and the rank approximation. So if you take a 100 rank 100, this is how it looks like. So let us change this to another value, say rank 10, and see what sort of reconstruction it gives. As you can see here, it was very blurry. A lot of components are missing, but this is a more compressed version because we are only using the 10 singular values. When we use for example 50 singular values, we get result something like this. It is almost clear. It is but slightly lesser compression as compared to rank 10 singular values. And then if you try to represent, say, using 500 singular values, it would look exactly similar to this. So in this way, by actually modifying the k, we can appropriately choose control the number of singular values and thereby reconstruct the image of arbitrary compression levels with little at the cost of little degradation in the quality. So this is how image compression using SVD can be done by using a low rank representation.